Okay,
awesome. So welcome. Thank you so much, Coco. So welcome back, everybody. It's so lovely to have you all with us here again this Tuesday afternoon. And of course, a big warm welcome to all those people that are new today. You are joining us in our sort of second to last lesson on this particular section. But hopefully, if you've done Euclidean geometry at school, then you will at least still be familiar with what it is that we're doing over here. So if your school is working according to the national ATP, which they probably are, you would have done Euclidean geometry by now and you would have moved on to trig. All right, so the reason that I've got this first question up is because this is something that I mentioned last Thursday. And I can't remember the student that asked me to do this, but hopefully you're with us tonight. The reason that we're actually doing this question matrix is really because of question number 4. I had done a similar question last week where we had to work out the ratio of the area of one triangle over the area of another triangle. And we had used the formula for the area of a triangle, half base times height. But unfortunately, that's not going to work with this particular pair of triangles because we don't know the perpendicular height for one thing. So it means that we're going to have to use something else. And that's why I said I would do this question, because here I'm going to show you how we could also use the area rule. All right, so that's really why I'm doing this question. It's not because we want to answer 1, 2, or 3. We should all know how to do that by now. But it's really because of question 4. So let's just get to that point fairly quickly. Reading the information, it tells us in triangle ABC, P is the midpoint of AC. So what does that mean? When they say that P is the midpoint of AC, what do we read from that? What does that mean for us? Does anybody want to tell me what they think that means? So if P is the midpoint of AC, then it means that?
It means that AP and PC are equal.
Beautiful. Thank you, Tando. Excellent. Okay, so AP and PC are equal to each other, 100%. The other thing that they tell us here is that RS is parallel to BP. RS is parallel to BP. Okay, and that will be along the entire length over here. All right, lovely. So now that they've given us parallel lines, what does that mean for us? We've got triangles, we've got parallel lines. What should we start thinking about? It means we need to start thinking about proportionality, intercept, theorem. Okay, so probably, yes, exactly, Jamie. There's probably something going on with proportionality in this question. All right, then we read a little bit further and we learn that the ratio of AR is to AB is 3 is to 5. So let's go ahead and go and put that on the diagram. Okay, so AR is this line over here. So AR is 3 is to 5 is the whole thing. All right, now what they are saying is that the ratio of AR is to AB is 3 is to 5. They're not telling us that AR is 3 units long. They're not telling us that AB is 5 units long. It could be a different length to that. We just know something about how the sides are divided. Interestingly enough, if from A to R is 3 and from A to B is 5, what's this little bit over here, RB? What would it be?
2.
It would have to be 2, quite right, to be there. All right, so now we can write RB is to RA, or we can write something about BR is to AB if we wanted to, but we'll just have to wait and see what the questions ask us. So the first question says to us, determine AS is to SP. So they want a ratio from us. AS is to SP. Anybody got an idea of what we would do here? What is AS is to SP? Which triangle are they asking us to work in?
Triangle ABP.
A triangle ABP, absolutely. Okay, because here we've got this line over here parallel to that one over there. So quite right, they want us to work in triangle ABP. Perfect, right? So now we look in triangle ABP, and we can see that AS over SP is the same as AR over
RB.
RB, absolutely. Okay, so let's say that, all right? So AS over SP is the same as AR over RB. Reason? Proportionality intercept theorem. And that's because RS is parallel to BP. Okay, so we know that AS is 3 and AR is 3, and RB or SP, that's going to be 2. All right, everybody happy with that?
Yes, ma'am.
All right, good stuff. Part number 2, AS to SC. So AS is this one over here to SC. So AS, okay, Maseko, go for it.
No, ma'am, it's okay. It was a mistake. Sorry.
Was it a mistake? Okay, all right. No, that's fine. If you wanted to say something, that's absolutely fine. What does AS have to be, though? AS has to be 3 as well, doesn't it? So, I mean, if we wanted to, we could call this 3x. We could call that 3y. I mean, whether you put the letters there or not, it really doesn't make any difference. But that would be 3x, okay? Then we know what SP is, don't we? We know that SP also has to be 2x, all right? So now the only bit that's missing is going to be PC.
PC.
Can we see that? So PC is missing here. Is there a way in which we can work out what PC is going to be?
Yes, as AP is equal to PC. So if we add AS and SP, which is going to be 5, that means PC will also be 5.
Was that you again, Tando?
It's Anza, ma'am.
Anza, sorry, Anza, I didn't see that. Anza, that was fantastic. Okay, well done. I'm so pleased. All right, that is exactly the whole idea here. So this is why I was saying to you in the beginning, when they tell us P is the midpoint of AC, what does that mean? And we needed to know what it meant, because otherwise we wouldn't be able to answer this question. Perfect, Anza, I love it. All right, so AP is the same as PC. So that means that PC, so AC equals PC, that's been given to us. Okay, so therefore PC is also going to be equal to 5x.
Ma'am, it's AP. It's AP, not AC.
Oh, sorry. Thank you so much. Quite right. At school, do you know what I always say, Anza? I tease the boys I teach, and I say, I made that mistake on purpose to see who was paying attention. Anyway, I can't claim that right now. All right, so AP equals PC. Perfect, thank you so much. And that means that PC is equal to 5. Lovely, great. So that means that, so therefore, AS is to SC, in this case, is going to be 3 is to 7. Okay, Matrix, everybody happy with that?
Yes.
Okay, all right. So let's do the next one. RT is to TC. Okay, so let's go and highlight those lines. Okay, so here's RT and here's TC. What is RT over TC equal to, Matrix? In which triangle are they asking us to work? I suppose is the other question we should be asking.
Triangle SCR.
Triangle SCR. SCR, perfect. Yes, 100%. That's exactly the right triangle. There's just Coco. Please will you just answer Atule in the chat?
I'm busy typing at the
Oh, you're
moment.
busy typing. Okay, all right. Sorry. Thank you very much. Okay, so Atule, Coco will address your question now. All right, perfect. So we are working in this triangle over here because we have side TP or line TP that is parallel to side RS. Okay, good job. So we know that RT over TC is going to be the same as RT over TC is the same as
SP over
SP.
PC.
Beautiful, SP over PC. Okay, and again, we would say proportionality intercept theorem. Name our parallel lines. Let's just move this up a little bit. That's because RS is parallel to TP. Okay, so now we can go ahead and go and fill that in. SP we know is 2 and PC we know is
5.
excellent. Thanks, Tobile. Good job. Okay, so now we've done all the quick and easy stuff. Let's now go and have a look at area TPC over area RSC. Now, in this particular question, there I'm just going to rub some of that out so that I can highlight this a little bit better. Okay, so in this particular question, what is different here to what we saw last week is that there is no perpendicular height. Okay, so in other words, there's no height between parallel lines that we can use. So half base times perpendicular height is not going to work in this case. The other hint that we need to use the area rule rather than the area formula is the fact that these two triangles share an angle. Okay, so now I've highlighted them both in blue. Here's TPC. This is TPC over here, right? And RSC is this one over here, just inside. Okay, all the blue. What angle do they share?
C.
Angle C.
They do. They share angle C1, don't they? All right.
Yes.
So that means that we could use the area rule. Do you remember what the area rule is from grade 11?
No.
Okay. All right. So if you have, let's go over to the side and then we can come back and we can talk about this. Okay. So it will be on your formula sheet. And it is something that you will obviously do later on this year. Normally we do 2D and 3D trig either the second term or the third term. So your teachers will go over this with you again. All right, so if this is triangle ABC, not very exciting, right? That means that opposite angle A, this side over here, side CB, I can call that little a. And opposite angle B over here, I have side little b, so side AC is also called side B. And opposite angle C matrix, I have side little c. Okay, so that's very important to know how we name the sides in relation to the angle. Okay, so opposite. So in other words, a side is named according to the angle that it is opposite from. So if we are working with, let's say, angle A, all right, I know how big A is and I want to work out the area of triangle ABC. I need to know how long B and C are, little b and little c. All right, so it works like this. Half, because it does come from the other formula, half BC sine A. Okay, that's if I know angle A. And if I knew how long B and C were. all right? But I can use it in 3 different ways. I could also say half CA sine B, if I knew angle B. And the other way that I could use this is if I knew side A and B and I knew the size of angle A. So in other words, half AB sine C. Right, so it just depends on what information I have. All right, but it has to be a side angle side situation. Okay, so a side, the included angle, and another side. Does that make sense to you? So all of these here are side angle side. Does that make sense, Matrix?
Yes, ma'am.
Okay. Everybody else, you happy?
Yes, ma'am.
Okay, so if we now go back and we have a look at what we've got over here, we can see that they share angle C1, all right? So now, we're not going to be able to use perpendicular height. We don't have a perpendicular height. We're going to have to use the area rule. So subbing into the area rule, all right? So now for the top for area triangle TPC, that will be half. Okay, so another way of looking at it is that this side over here would be side little c. I suppose that would be side little t, that would be side little p. We could also call this whole thing little s. I don't know if we would need to do that. It's probably better for us to name it. You know what? That's going to make things confusing. Let's just work with the letters that we've got, all right, instead of trying to make things confusing. Okay, so we've got angle C1. Right, so in triangle CPT, which 2 sides are next to angle C1? What are they called?
Side PC and side TC.
Good. So half PC times TC sine C1. Awesome. Well done. Okay, now at the bottom, same story. Half, okay, then this whole side over here and that whole side over there, so that would be SC. This whole side would be RC sine C1. Okay, Matrix, and then of course anything divided by itself is 1. Anything divided by itself is 1. So that means that we're going to end up with PC times TC over SC times RC. Now, we've worked out what these various things are in 1, 2, and 3. So let's go back and have a look. What was PC? PC was?
5.
5. Good. And TC was?
2x.
TC? TC would also be 5, wouldn't it?
Yes.
Yeah.
Okay, so it would also be 5. It might be 5A or whatever the case is, but it would also be 5. This over here would be 2A if we decided that that side was A. All right, so it would be 5 times 5 over SC is 7. Exactly, and RC is also 7. So that would be 7 times 7. Okay, so that gives us 5 times 5 is 25 over 7 times 7 is 49. Coco?
Yes, ma'am.
The hospital's just phoning me. Just give me 1 second.
Sure. All right, guys, our apologies. I think Lee's son is actually in hospital at the moment, so she just needs to check on him. But I'm going to try and get something else up on the screen so we can actually continue working. In the meantime, is there anybody who has any question on this particular question that we just did concerning questions 1, 2, 3, and 4? If you do, you can raise your hand now or unmute and say, ma'am, I don't understand how we got to this particular part. And we can look at that part again. Okay, and she's back. All right.
Here we go. Sorry, guys, my not that we need to talk about this, but my son hurt himself playing sport today. So he's gone off to the hospital. So that's why I'm sorry I had to run off and just take that. But anyway, let's get back and carry on doing maths. Is everything okay? Is there people that are confused, Coco?
Dalen, I think Dalen may have a question. His hand is up.
Sure. Okay, Dalen, go for it.
Must they bother when you ask you of PC, would they give a method to you, or you must have to wait?
Just say that again, Dalen. I didn't understand.
When you ask you table of PC times TC sin
Yes.
angle, would they give a method to you, or must you remember it?
No, you need to remember it. So you would need to know or be able to look it up on your formula sheet, Dalen. Okay, so this formula for the area of a triangle is on your formula sheet. The one that they don't tell you is the one that we used when we were in grade 8, grade 9, which is half base times height. That is not on your formula sheet. So that one you absolutely do need to remember.
Okay, thank you, Miss.
Okay, it's a pleasure. It's an absolute pleasure. Okay, guys, so I'm glad that we had a chance to go over that, and I could at least show you how we could sometimes use the area rule as well. Often we wouldn't be thinking about trigonometry and Euclidean geometry, but they are connected. So, you know, I just thought it would be nice to point that out to you. All right, what I'd like to do now, if there are no other questions, is continue with an exam type question. And what I'd like to do, okay, so when do you know that you should use that formula? So Nali, you would know if there was an angle in common. So let's say they shared an angle, then you would be able to use that formula. If they didn't share an angle, then you wouldn't. Also, if you were unable to write down whatever the perpendicular height is, then you probably would also need to use the area rule, but it would be more based on if there was a common angle. So if there's not a common angle, do half base times height. If there is a common angle, it's probably area rule. Okay. All right, so if we have a look at this question, this came out of a March paper, so that would have been a supplementary paper back in 2017, and I just absolutely love this question because it's just got a bit of everything in it, and it's a nice challenging question. So the reason that we're doing this really is because of question 3.3.2, but we've got to do all the other stuff in order to be able to get there as well. Now, the other reason why I love this question is because it asks us to prove that TPLN is a cyclic quad. And if you guys are anything like the matrics that I teach every day, I know that proving a quad is cyclic is something that often trips us up. And it is definitely something that you will be asked. Definitely you will be asked to prove that a quad is cyclic. So, you know, I think if you are able to do that, it's going to be really nice for you. Bearing in mind, this would be the very last question in the paper, but can you see here that's out of 3 marks? Okay, and of course we want to try and get all the marks that we can. So before we dive in and we start talking about how we're going to prove that this quad is cyclic, let's just read the information, and then we can talk about what that means on the diagram, and then we can try and get some ideas on how we're going to prove that TPLN is cyclic. Hopefully this is big enough and everybody can see. So in the diagram, LK is a diameter, all right? So who thinks the word diameter is an important word? Hey, I certainly do. When we see the word, yeah, so when you see the word diameter, what do you start thinking about? Cassandra, what do you think about when you see the word diameter? What does that mean to you?
The sum of 2 radii.
Indeed, absolutely. So in other words, it means that LP equals PK. Cool beans. That's definitely one thing that it means. So LP equals PK. Cool. What else does it mean? Someone else has raised who else has raised their hand? I can't see.
Ma'am?
Yes. Go for it, Watobe.
Does it also mean that N2 is 90 degrees?
Oh, well done. Good spot. So did you hear that, everybody? Watobe said, does it also mean that N2 is 90? It certainly does. Okay, it means that angle N2 is 90. And what's the reason for that, Watobe? There's a...
It's because the diameter, I mean, angles in the same segment. Is it right?
You're very You're very close, Tundlewaiter.
Can
We
I
call this
try, ma'am?
yeah, go for it, Siatemba.
In a semicircle, I mean in a
Wait,
semicircle.
okay. Angle subtend at 90 degrees.
Yes, absolutely. So we say angle in a semicircle. All right,
Yes,
good job, well done. Okay, so this is angle in a semicircle. Good job, Matrix, nice one. Okay, so that's the other thing that it means if they tell us that there's a diameter. Because they have identified that there is a point, we might also have angle at center is twice angle at circumference, but it doesn't look like that's going to be possible in this particular diagram that they've given us here. Okay, so let's leave that for now and let's carry on reading. Now, next thing, RNS is a tangent. So the moment we see the word tangent, I don't know about you guys, but immediately my mind is humming. What do we think about when we see the word tangent, Matrix?
Canal.
Go for it, Julie.
Tan-chord theorem.
Tan-chord theorem. You guys are perfect. We think about tan-chord theorem. Okay, 100%. Also, could be tangents from the same point? No. Could we have radius perpendicular to tangent in this case? Also no. Okay, so it's just going to be tan-chord theorem. All right, so we need to look out for that. Then they tell us that TK is a point, sorry, T is a point on NK, fine, and that TP is perpendicular to KL. All right, they put that in there for us. All right, so that TP is perpendicular to KL. All right, and they've shown us that over here. We can see that that's a right angle, so that's fine. The last bit of information, PLN is X, and they've done that on the diagram as well. Okay, so here's our X over there. Okay, well, that's quite a lot of information they've given us. Let's go and see what it is that they want us to do. So the first thing is that we need to prove that TPLN is a cyclic quad. Now, Katleho, you said that angle N3 is equal to angle L. It is. Quite right, it is. Quite right. Okay, so angle N3 over here would also be equal to X, okay, because of tan-chord theorem. I don't know if that helps us prove that TPLN is a cyclic quad, but I'm sure it's going to be useful for us later on. All right, so now there are three ways, Matrix, if you remember, three ways that we can prove that a quad is cyclic, okay? What are they?
Opposite angles and supplementary.
Okay, Anza, you're leaving out a very important word. Tisha, go for it. Go for it, Tisha.
You can unmute Tisha and you can speak.
Angles in the same. I'm saying that it does prove.
Okay, but again, you've left out an important word here. All right, so we want to prove that a quad is cyclic, we have to say converse. Okay, so converse angles in the same segment. All right, good. The other way that we can prove it, converse exterior angle of cyclic quad
Is equal to the opposite angle.
Is equal to the opposite interior angle. Quite right, Coco. And then the last reason is?
Converse of opposite angles of a cyclic quad.
Perfect, or supplementary. Good, Anza, that's lovely. Okay, so converse.
My apologies, Leah. I actually thought I was muted. I should not have answered. I'm unmuting myself again.
That's fine. That's fine. We love participation. You know this. Converse opposite angles of cyclic quad are supplementary. Okay, so Matrix, please, 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 you have to learn these off by heart. Okay. Converse angles in the same segment, quite right, Tabile. So these are the three reasons you can prove a quad is cyclic. There is no other way to do it, right? Maybe your teachers at school have taught you different words, but it's exactly the same concept. There is another way to say converse angles in the same segment. There is another way to say converse exterior angle of cyclic quad. I don't like to teach it saying something else because I feel that learning angles in the same segment and then converse angles in the same segment is easier for students. So this is how I've always taught it, right? But it has to be converse. It has to be converse because you're proving that the quad is cyclic. It's not given to you, all right? So if we go back and we have a look at what they've given us here, TPLN is a cyclic quad, right? So get your highlighter and highlight TPLN and let's see what we can see inside here. All right, so TPLN, so that's this over here, T. All right, okay, so now there is no bow tie inside that quadrilateral. So because there is no bow tie inside that quadrilateral, that means that converse angles in the same segment is not going to work in this case. Okay. The other thing that we can consider here, Matrix, if we go back and we look at the diagram, all right, is that we do have an exterior angle of the triangle, of the cyclic quad. So this angle over here would be an exterior angle of the cyclic quad. And this angle over here would also be an exterior angle of the cyclic quad. All right, because one of the sides of the cyclic quad has been extended, right? We don't really know anything about T2 or what T2 is equal to. So my guess is at this stage that that's not the one that we would use. But we do know something about angle TPK. What can you tell me about angle TPK, which I've highlighted in pink?
It's equal to 90 degrees.
It's equal to 90 degrees, absolutely. All right, and it's equal to 90 degrees because of adjacent angles on a straight line. So we could say that TPK is 90, and we can say that N2 is 90. Remember, in the beginning, Anza told us that N2 is 90 because of angle in a semicircle. So if N2 is 90 and TPK is 90, it means that TPLN has to be a cyclic quad because of converse exterior angle of cyclic quad. Right, so that's one way that we could do it. Does that make sense to everybody?
Ma'am, may you please explain that one more time for me?
That's fine. I'm going to write it all down. Okay, so in 3.1, no problem. All right, so in 3.1, okay, we have already stated in the beginning that angle N2 was equal to 90. Okay, do you remember that, guys? Angle N2 was equal to 90, and the reason for that is because the diameter subtensor, right angle at the circle, otherwise known as angle in a semicircle. Okay. We also know that TPK is equal to 90 because of adjacent angles on a straight line. Remember, they told us that TP was perpendicular to LK. So that means that this angle in pink over here also has to be 90. Let's get rid of the pink and let's put a 90-degree corner there as well. So what this means for us, Matrix, is this. This angle over here, N2, that I'm just busy coloring in at the moment, right, is equal to this angle over here that I'm also busy coloring in at the moment. Those two angles are equal because they're both equal to 90. All right, so that means that N2 equals TPK. Right. And if N2 equals TPK, it means that TPLN is cyclic. So therefore, TPLN is cyclic because of this over here. Right. And we would use the words, the reason, converse, exterior angle of cyclic quad. Okay, so because we've been able to prove that the exterior angle of this quad, in this case, this angle over here, TPC, is equal to this angle over here, N2, that means that this quad has to be a cyclic quad. So in other words, we've proved that it's possible for us to draw a circle through LNTP. Not that there is one drawn, we've just proved that it's possible. That's what it means when we prove that a quad is cyclic. Is everybody happy with that?
Yes.
No, okay, Nali. All right. Any questions?
Sorry, ma'am.
Yes, Tisha.
Ma'am, aren't you supposed to have two reasons to prove that a shape is a cyclic quad?
No, Tisha, you only need one. So either it's got to be one of those three that we discussed in the beginning. Okay, so either converse angles in the same segment, or converse exterior angle of cyclic quad, or converse opposite angles of a cyclic quad are supplementary, which you could also do in this case. We would also be able to do it that way here. I was actually going to talk about that next. Okay, but you only need one.
Okay, thank you.
Okay, all right. So the other way that you could have done this question if you wanted two matrix. Yes, Zianda, absolutely we can. All right, so Zianda, what we would have had to do in this case over here is we still would have had to start in the same way. Okay, so Zianda, this is for you up here. I'm writing 3.1, so this is the alternative. We would have still had to say that N2 is 90 because of angle in a semicircle. Then we could have concluded that TPL is 90, and that was given to us. Remember, they told us that TP was perpendicular to KL. So now we can conclude, Zianda, that N2 equals TPL, and therefore TPLN is cyclic. And exactly as you had said, the reason here, which I should be writing over there, should be writing it next to it, but I'm going to write it underneath because of space constraints, is converse. Opposite angles of cyclic quad are supplementary. Okay, well done, Zianda. I'm so glad you saw that. All right, so there are two ways in which we could have done 3.1. Okay, in this case, converse exterior angle of cyclic quad works, and converse opposite angles of a cyclic quad are supplementary, also works. Oh, hang on a second. I've made a mistake. Wait. Sorry. Hang on a second. I did something wrong here. It's not equal to. They sum up. Sorry, my mistake here. So N2 plus TPL equals 180 degrees. Sorry, not that they equal. They add up to 180. Okay, so just change that. N2 plus TPL equals 180. So therefore TPLN is cyclic. Converse opposite angles of a cyclic quad are supplementary. All right. So now that is 100% correct. Okay, everybody happy with that? Are there any questions? Sure, okay, all right. Well, if there are, please go ahead and ask, no problem. We've done 3.1. Let's go on and do 3.2. So now in question 3.2, they have asked us for the size of N1 in terms of X. All right, so they want N1 in terms of X. So here's N1 over here, matrix. Here's N1. What's N1 equal to?
Equal to K, ma'am.
It is. It's equal to K. Who said that?
Michaela.
Oh, Kayla, well done. That's great, Kayla. 100%. Okay, and the reason that they are equal, Kayla?
Tan chord theorem.
Beautiful. Well done. Thank you so much. Now, how are we going to relate angle K to what we know about X to something else that we know? Where are we looking, Matrix? So from K, where do we look?
Ma'am, do we look at L?
We do, Cassandra. So from K, we look to L because we know that that's X. And then we look down to N2 because we know that that's 90. And we can see that angle K is an angle inside triangle KLN. Okay, and that's useful to us because angle K plus angle L plus angle N2 has to add up to 180. Right, so that's how we're going to get our solution in this case. What I'm going to do is I'm going to rub this out and just give myself a little bit of space to write here. Okay, so identify the angle and then ask yourself, what is this angle equal to? And then from there, try and figure out how that is related to X and anything else that you may already know at that stage. All right, so 3.2, let's put this down. So here's 3.2. Kayla, you said to us, angle N1 equals K. Beautiful. All right, and you said tan chord theorem, which is 100% correct. Okay, then we looked in triangle KLN, all right, and we can see that if we add K to L to N2, we will end up with 180 degrees, okay, because they are the interior angles of a triangle, and we know that they sum up to 180. So K is what we want. L we know is X. N2 we know is 90. So now we're going to take the X and the 90, we're going to take those two terms over to the other side. So that means that K is going to be equal to 180 minus 90 is 90, and then when the X comes over, minus X. Okay, does that make sense to everybody?
Yes, ma'am.
Okay, good, Relebogile. You sure? Matrix, you sure? No one's got any questions?
Ma'am?
Yes.
Yes, go for it.
Ma'am, can you treat the tangent as a straight line, and instead of using the tan chord theorem, say that N1 plus N2 plus N3 is equals to 180 degrees because of angles on a straight line, and then you get 90 minus X.
Absolutely. So, but what you would have to do there, can you see there, this is amazing. I love it when my students do this because now you really are thinking. So just like there was more than one way to do question 3.1, there's more than one way to do question 3.2. All right, brilliant. But what would you have had to say first? Can you see there? You would have had to state that angle N3 was equal to X. Okay, so I don't know if you remember, we were talking earlier and someone, I can't remember who it was, someone said that N3 was equal to X, which is true. So your way of doing this, we'd first have to state that N3 was equal to X because of tan chord theorem. And then you could say that X plus N2, which is 90, plus N1 adds up to 180 degrees. Lovely, well done. Let's just quickly put that down. Brilliant. Okay, lovely way of doing it. Yes.
Correct me if I'm wrong, but they did ask for N1, yes, in the question before. So we cannot give them an answer based on K. We are then going to have to continue that and say, therefore, N1.
Yes, sorry. So N1 is equal to K. Yes. Sorry. So N1 is equal to K because of tan chord. Thanks, Coco. Sometimes the old brain doesn't work so well. Okay, and therefore N1, correct. N1 is equal to 90 minus x, absolutely. Okay, so then the other way that we could have done this with what Kanisile was saying, which was 100%, is we would have concluded that N3 is x because of tan chord theorem. And then we could say that x plus 90, which is N2, plus N1 adds up to 180 because of adjacent angles on a straight line. I think this is going to be quicker. And therefore, angle N1, which is what they asked us for, take the 90 and the x over, would be 90 minus x. Yeah, that was much faster, wasn't it? Okay, so yeah, two ways that we could have done that as well. The second way was a little bit faster, which is really nice, but the first way, nothing wrong with that either. Everybody happy?
Yes, ma'am.
Okay, all right, thank you. Okay, so now matrix, let's jump into these questions here. First of all, we need to prove that KTP is similar to KLN. Right, so I'm going to rub this off. Right, so when they tell us which triangles to prove are similar, they are giving us massive, massive, massive hints. All right, remember we've had this conversation before, matrix. All right, they are telling us that angle K and angle K are equal. They are telling us that angle T and angle L are equal. They are telling us that angle P and angle N are equal. We just need to figure out the reasons, right? And that means that KT is this, well, KT corresponds with KL and TP corresponds with LN and KP corresponds with KN, but we'll get to that just now. All right, so KTP is this triangle over here. So let's just, ooh, that's not a very good line. Ugh, sorry, guys. Not drawing very well. Okay, there's KTP and KLN, oh, is the big triangle. Okay, so it fits inside. Okay, so KLN is our yellow triangle, which I'm now drawing red around. Okay, so let's get started. In 331, in triangle KTP and triangle KLN, can anyone tell us one angle that we already know is equal? So I think there's lots going on in the chat. There we go. Exactly. Well done, matrix. Okay, so angle K is common. All right, it's in both. So K is common. So that's the first angle. Okay. Second angle.
N2 is equal to TPK.
Good, Jamie. N2 is equal to TPK. All right, and that's because they both equal 90. Remember over here, we said that TPK was equal to 90, and we also said that N2 was equal to 90. So here we could say proved in 3.1, or I suppose we could say both equal 90.
Ma'am, do you have to say that it was proven in 3.1?
You are
say it was proved?
You know what, Kayla? I think if you just said proved above, that would be fine. Okay, but you are supposed to explain why. All right, and now the third one. Okay, so KN, so that would be angle L. Yes, who's talking?
Can we say that angle N2 is equal to TPK because of what's this? opposite angles of a cyclic quad. No, what's the extra angle of a cyclic quad?
Absolutely, absolutely, Anza. 100%. That's another thing that we could have said there. Yeah, 100%. So here, all we could have said, or exterior angle of cyclic quad. Excellent spot. Well done. Okay, so proved in 3.1, or they're both equal to 90, or exterior angle of cyclic quad. Now that we've proved that the quad is cyclic. Perfect, Anza. Good job. Nice. I really like that. Well done. All right, and then we have got that was x. This was equal to 90 minus x, wasn't it? That was k. All right, so then that means that the last angle in the big triangle, L, has to be equal to T2, doesn't it?
Yes.
Okay, and that is because of remaining angles of a triangle, or third angle of a triangle, or interior angles of a triangle, or whatever it is that your teacher has told you. All right, so I go angle, sum, and triangle. Okay, but you're not allowed to do that first. Okay, angle, sum, and triangle, you can only use that as your third reason. Okay, so now very carefully, KNL, so triangle. Mind you, they've already given us the order over there, so it doesn't really matter. KTP is similar to triangle, KLN. All right, and our reason, angle, angle, angle. There we go. All right, so now let's get into this monstrous question, because that's the one that I really want to do with you guys. Okay, last bit. So KT times KN, this is what they want us to prove, equals 2KT squared minus 2TP squared. How should we approach questions like this?
Ma'am, can you write KT over KL is equals to TP over LN, which is also equals to KP over KN?
Absolutely, absolutely. That is exactly the right way to approach this. So now they're talking about the sides. Okay, so now that they're talking about the sides, we need to write something about the sides. So that was 100% perfect. That is where we're going to start. Now, what I'm going to do here, Matrix, is I'm going to rub out what we've got in question 3.1, just so that we've got space to write. So now, as a result of proving that these triangles are congruent, so similar. So from this over here, right, that I'm highlighting in yellow, right, we will now conclude that KT over KL is equal to TP over LN is equal to KP over KN. Okay, so first two over first two equals last two over last two equals first and last over first and last. All right, and here, corresponding sides of similar triangles in proportion. And now let's highlight what it is that we need. Okay, remember in our question, it had a KT. Okay, so we've got a KT over here. It also has a KN. So we've got a KN over there. So that's looking at the left-hand side of this. So I've got a feeling then, Matrix, that they want us to work with the first one and the last one. So let's get those two together, all right? So that means that KT over KL is equal to KP over KN. Then they've cross-multiplied because they've got KT times KN. So they've multiplied those two together. So what that means for us, Matrix, is that KT times KN is KP times KL. Now, a strategy for solving a question like this is now that you have seen what the left-hand side is equal to. So in other words, KT times KN. Can you see that it's equal to KP times KL? Let's try and see if we can prove that KT squared minus TP squared, obviously both multiplied by 2, whether that's equal to the same thing. all right? Because if we can prove that two things are equal to the same thing, then we've proved that they are equal to one another, all right? So now we're on a mission. We want to see, all right, how we can show that 2kt squared minus 2tp squared could be equal to kp times KL. Now, looking very carefully at KP and KL, all right? Now, someone said this in the beginning, and I can't remember who it was, right? But let's just get rid of that. Remember that LK is the diameter. Okay, and we had said at the beginning that LP equals PK. Because they are radii. So that is going to become important for us as well. Okay. The other thing that we can see here, they're talking about KT squared. Okay, so KT is this side over here that I've done in pink. TP squared is that side over there. So KT squared minus TP squared, where have we seen something like that before? From what have we, and we can see that there are two sides of a triangle. We know that this is a right angled triangle. So what could we say?
Ma'am, we could use Pythagoras theorem.
Pythagoras, absolutely, absolutely. So we can see, matrix, that PK squared or KP squared, okay, plus PT squared is going to be equal to TK squared or KT squared because of Pythagoras. So here they've got KT and they've got TP on the same side. So let's take TP or PT over to the other side so that it can be with KT. So that means that we've got KP squared on its own, and it's equal to KT squared minus TP squared or PT squared. Right, so we're getting ever closer. Right. Now, matrix, if we go and have a look, they said KP times KL. KP times KL. So as far as KP times KL is concerned, we can see that KP is equal to KL. So if we are talking about sorry, I've just lost my train of thought now. Hang on 1 second. 2 KP, we need to double KP. I've realized what it was that I needed to say. Okay, so KL, so going back to this line over here, okay, KL is equal to 2 of KP. Does that make sense to everybody? KL, the whole diameter, is equal to 2 radii, 2 of KP. Does that make sense, everyone?
Yes, ma'am.
Okay.
Yes, ma'am.
All right. So
I'm seeing some shaking heads, ma'am.
Pardon?
I'm seeing people shaking their heads. Some people don't understand how.
Okay, so KL, remember KL is the diameter, matrix. So let's go back here. KL is the diameter. Okay, so this piece of line segment and that piece of line segment are equal to one another. All right, so instead of me describing this as 1 of KL, I can describe this green line as 2 of PK or 2 of LP? Does that make sense?
Yeah, well.
Okay, so KL, the whole diameter, is 2 of KP. So what this means for us, coming from this line where I've written over here, so that means that KT, whoopsie, let's just change the color. So KT times KN, I'm subbing into this, all right, that I've discovered, all right? I know that KL is 2 KP, so that's going to be KP times 2 KP. So in other words, I'm subbing in place of this. Okay, so KL is equal to 2 of KP. So that means that KT times KN is equal to 2 KP squared. Okay, now coming back to this line over here. All right, I can say that 2 kp squared, because I can multiply through by 2 kp squared will be equal to 2 kt squared minus 2 tp squared. I've just multiplied through by 2. All right, so therefore I can now conclude that they are both equal to the same thing. So kt times kn is equal to the same thing as 2 kt squared minus 2 tp squared, which is 2 kp squared. So now I can conclude that kt times kn is equal to 2 kt squared minus 2 tp squared. Okay, is that all right, Matrix?
Yes, ma'am.
Awesome. Mind blown. Okay, so at least we've been able to do a problem-solving question.
And we are unfortunately out of time.
And we are unfortunately out of time. Yeah. Coco, do you mind if I leave you to say goodbye? I just want to go and see how my son is. He's just messaged me and I just need to see if his ankle's okay.
Not a problem. Thank you.
Is that okay? Thank you so much. Thank you, Matrix, and we'll see you on Thursday, hopefully drama free. Have a wonderful